subatomic particles.
Formulation of Hamiltonian mechanics.
Hans Christian Ørsted discovered in 1820 that electric currents create magnetic fields, which marked the first connection between electricity and magnetism. Ørsted's work laid the foundation for understanding how electric and magnetic forces are interrelated. André-Marie Ampère built on Ørsted's discovery by developing mathematical formulations for the interaction between electric currents and magnetic fields, leading to the foundation of electrodynamics. Michael Faraday discovered electromagnetic induction, showing that a changing magnetic field could induce an electric current. Faraday's work is pivotal, as it underpins modern electric generators and transformers. James Clerk Maxwell formulated Maxwell's equations, unifying electricity and magnetism into the single framework of electromagnetism. His equations predicted the existence of electromagnetic waves, setting the stage for the development of modern communication technology. Work of these scientists revealed the deep connection between electricity and magnetism, uniting them into a single field. Maxwell's equations are considered one of the great achievements of classical physics, explaining how light, radio waves, and X-rays are all forms of electromag. Sadi Carnot developed the Carnot cycle, which describes the theoretical maximum efficiency of a heat engine. His work was foundational in the field of thermodynamics, shaping early understanding of energy transfer. Rudolf Clausius introduced the concept of entropy and formulated the second law of thermodynamics, describing the direction of heat flow and the natural tendency toward increased disorder in isolated systems. Lord Kelvin contributed to the formulation of the first and second laws of thermodynamics. He developed the concept of absolute temperature and the Kelvin scale, fundamental to thermodynamic studies. These discoveries defined the laws governing energy, heat, and work, forming the core of thermodynamics. This field became essential in various industries, especially in understanding engines and the broader concept of energy conservation, which affects all physical processes. Young conducted the famous double-slit experiment, demonstrating interference and showing that light behaves as a wave. His work was crucial in establishing the wave nature of light. Augustin-Jean Fresnel built upon Young's findings and mathematically described diffraction, further confirming light's wave properties. Fresnel's equations describe how light behaves at surfaces, paving the way for optics and photonics. The wave theory of light explained many optical phenomena and laid the foundation for understanding electromagnetic waves. This understanding would later be integrated with Maxwell's equations to explain the full spectrum of light. Rowan Hamilton developed Hamiltonian mechanics, which provided a new formulation of classical mechanics using energy functions rather than forces, offering a powerful tool for analyzing physical systems. His work became essential to later developments in quantum mechanics. Others, the work of many 19th-century physicists, expanded on Newtonian mechanics, refining equations that describe planetary motion, oscillations, and more. Hamiltonian and Lagrangian mechanics advanced the study of motion and forces, establishing principles that would later integrate into quantum mechanics. J. Thomson identified the electron through experiments with cathode rays. He discovered that these rays consisted of negatively charged particles, which he named electrons, fundamentally changing the model of the atom. The discovery of the electron marked the beginning of atomic physics and the understanding of subatomic particles, reshaping atomic models and forming the basis of quantum theory. Albert Einstein, in 1905, developed the special theory of relativity, introducing the famous equation E equals mc squared, showing that mass and energy are interchangeable. In 1915, he published the general theory of relativity, redefining gravity as the curvature of spacetime. Relativity revolutionized our understanding of space, time, and gravity, explaining cosmic phenomena like black holes and the bending of light around massive objects, fundamentally changing modern physics and cosmology. Max Planck introduced the quantum hypothesis, suggesting that energy is quantized. His work was the first step toward quantum theory. Niels Bohr developed the Bohr model of the atom, explaining electron orbits and quantum jumps, pioneering atomic theory. Werner Heisenberg formulated the uncertainty principle, highlighting inherent limits in measuring a particle's position and momentum simultaneously. Erwin Schrödinger developed the Schrödinger equation, describing how the quantum state of a system changes over time. These scientists developed quantum mechanics, a theory describing the behavior of particles at atomic and subatomic scales. Quantum mechanics underpins modern electronics, chemistry, and many areas of physics, redefining determinism and predictability. Enrico Fermi conducted pioneering work on nuclear reactions, leading to the development of the first nuclear reactor. Otto Hahn and Lise Meitner discovered nuclear fission, the splitting of an atom's nucleus, which releases a tremendous amount of energy. Nuclear physics led to practical applications such as nuclear power and weaponry, with a profound societal and scientific impact. Georges Lemaitre proposed the idea of an expanding universe, originating from a primeval atom. Edwin Hubble observed that galaxies are moving away from each other, supporting the idea of an expanding universe. George Gamow predicted the cosmic microwave background, the afterglow of the Big Bang. The Big Bang theory describes the origin of the universe and has shaped cosmology, providing insights into the age, expansion, and evolution of the cosmos. Richard Feynman developed Feynman diagrams, visual tools that simplify complex particle interactions in QED. Julian Schwinger and Shinichiro Tomonaga co-developed the mathematical foundation of QED, describing the interaction between light and matter. QED became the first successful quantum field theory, describing electromagnetism at the quantum level with remarkable precision. It laid the foundation for the standard model of particle physics. Peter Higgs and Francois Englert proposed the Higgs mechanism, explaining how particles acquire mass. This theory was confirmed in 2012 through experiments at CERN. The Higgs boson discovery completed the standard model, explaining mass and helping unify fundamental forces, an essential milestone in particle physics. Feynman initially proposed the concept of quantum computers. David Deutsch developed the first quantum algorithms. Peter Shor created Shor's algorithm, showing that quantum computers could factorize numbers exponentially faster than classical computers. Quantum computing leverages principles of superposition and entanglement, promising to revolutionize fields such as cryptography, materials science, and artificial intelligence. Edward Witten, Leonard Susskind, and Juan Meldacena contributed to string theory and quantum gravity research. Meldacena's ADS-CFT correspondence provided a theoretical link between gravity and quantum field theory. These theories aim to unify general relativity and quantum mechanics, seeking a theory of everything that would explain all known forces and particles. Rubin provided evidence for dark matter through galaxy rotation curves. Saul Perlmutter, Brian Schmidt, and Adam Rees discovered the accelerated expansion of the universe, attributed to dark energy. These discoveries suggest that visible matter is only a small part of the universe, with dark matter and dark energy comprising the majority, reshaping cosmological research. LIGO scientific collaboration detected gravitational waves in 2015, confirming Einstein's predictions and opening a new way to observe cosmic events. Discovery of gravitational waves introduced multi-messenger astronomy, where gravitational and electromagnetic signals are used to study celestial phenomena. These discoveries represent monumental steps in physics, each one expanding our understanding of the universe and prompting new questions that drive the field forward. Physics continues to be a vibrant area of discovery, with these milestones forming the bedrock of modern scientific knowledge.